So in this week's homework video, we're going to extend and generalize a little bit some of the knowledge we've already accumulated about the topic of functions. So the title for today is Power Functions, and I've given you the German underneath, just in case you're interested. And this sounds like something new, but actually, as you'll see, it's something that we've seen already in certain specific examples, and today we can then generalize it to more general examples. So here you have the definition of a power function. So a function, f of x, is equal to a times x to the power of r, where a is any real number. So you're multiplying any real number by x to a power, and r is a rational number. So r could be 1, 2, 3. It could also be a fraction. It could also be a negative number, a negative integer, a negative fraction. So we have a lot of different possibilities here. These functions of this form are power functions. So write down this definition first, and we'll take a look together at some examples of power functions that we've already seen. So the first example of a power function we've already seen is this one here. F of x is equal to a times x. So in this example, our r, the power from here, is just 1. Because anything to the power of 1 is just the thing itself. And we know that this gives us a linear function. And in fact, because this goes through the origin, because we don't have a plus d at the end, we know that it must be direct proportion, an example of direct proportion. As x gets bigger, f of x gets bigger in proportion to each other. So it's direct proportion because it goes through the origin. So it's a very specific example of a type of linear function that we looked at last year. We also know that we can get important information from a. A gives us the gradient. So if a is positive, we have an increasing linear function, and if a is negative, then we have a decreasing linear function. So a tells us the gradient of these linear functions. A second example we've already seen is with x squared in it. Now we've also been looking here, like we have with linear functions of ax plus d, we've been looking at things times x squared plus times x plus some constant. So this is actually a simpler version of the types of quadratic functions we've already been looking at. So, as I've said, this is a quadratic. Function. Again, it must go through the origin because we're not adding anything. So if x is 0, f of x is going to be 0. And we know that it's going to take the form, the graph is a parabola. And it's going to have a kind of U shape. We know that if a is positive, then our graph looks like this, where we have this U shape upwards. And if a is negative, then we know that the graph is going to be a U shape downwards, also going through the origin. So we know that this is going to give us a quadratic with a parabola that looks either like this or this, depending on the size of a. And of course, the larger a is, the steeper this is, the closer together these two arms are, the more extreme and pronounced this U shape is. And the smaller a is, the more open the parabola seems to be. So that's the second example. Our third example, coming down here, is one we haven't looked at so much, certainly not in as much detail as linear functions or quadratic functions. And actually this is where we start to generalize things a bit more. But just to refresh your memory, this is a cubic function, because we're looking at x cubed, so r is 3 in this example, and we know that the graph tends to look something like a kind of S shape or a skewed S shape like this. So it comes up, it flattens out a little bit, it goes through the origin, and it comes up again in a similar way. It's kind of symmetrical in some ways, you can think of it as being. If I do it on here, then we'll be able to see it more clearly. You see this type of shape that we get here. That's a cubic function. And you see if I increase this here, it makes it steeper as well. So it makes it more extreme. And if I make a much, much smaller, then it becomes much flatter. Just like the parabola in the quadratic function. So these are 3 examples we've seen already. And actually, these are 3 examples for which r is an element of the natural numbers. And if r is an element of the natural numbers, then it's also called the degree of the power function. And in green here, I've given you the German as well. It's just a translation of degree, of course. So we can say that this is a 3rd degree power function, because we have r being equal to 3. This one here is a 2nd degree power function. And of course our linear function is a 1st degree power function. And this is often used in exam questions, particularly in the Matura. You're given a 3rd degree power function, and you should know that this represents a cubic function, that your biggest term or your biggest power in here is going to be x cubed. And if it's a power function, you know it doesn't have any other terms. So that's helpful to know this way round, that if you are given a 3rd degree power function, you can then write the equation of the function, including the a here. And if you have a look on page 30 of your textbook, it gives you a nice summary of the graphs of lots of different power functions. It starts from the power function f1 of x, which is x to the power of -5, and it goes all the way up to x12 of x, which gives you x to the power of 6. And if you could find that page in your book and take a look, I'd like to notice a few things about the graphs of the different power functions, because we can notice some patterns in how the graphs look, which can help us then to identify how graphs of functions should look, and so you can match equations to graphs much more easily. So first of all, let's look at the case where r is positive, where r is greater than 0. So when r is 1, 2, 3, etc., etc. Let me switch to black. So, for positive r, if r is even, so 2, 4, 6, and of course this pattern does carry on, then if you have a look at those on page 30, where you've got x squared, x to the power of 4, x to the power of 6, the graph is kind of U-shaped. You can notice that the U's are slightly different for each of them, but for them you do tend to get something that looks a bit like this. However, if r is odd, So if we look, for example, at 1 is a special case, it doesn't really hold. But if you look at 3 or 5, and again this pattern carries on, then you can notice as well that this kind of S shape, I mean S isn't really a good approximation for the shape, but you kind of know the shape I mean, this one that we had here. This shape is continued as well, or represented as well in the x to the power of 5 one. So if r is odd, the graph has this kind of shape. Apart from, of course, 1 where it's linear, but then it still increases all the time, just like the other odd powers do. And so these two shapes here are two different types of parabolas. So far we've only been referring to this shape as a parabola, but this one is an odd parabola. So this is an even parabola, and this is an odd parabola. So for r being greater than 0, we can expect parabolic graphs. So you know to expect, if r is even, we get this U shape, and if r is odd, we get this kind of increasing snake-like shape. And this is to be expected, really, because if you consider for negative x when r is even, if you raise a negative number to an even power, then we're going to get a positive result, because a negative times a negative is going to give us a positive result. Whereas with the odd ones, if I put a set of axes on here, that should go through the origin. Then if we have a negative x value here, then we're going to have a negative y value, because if I raise negative 2, for example, to the power of 3, that's negative 2 times negative 2 times negative 2. The result you're going to get as well is going to be negative. So we kind of expect that these ones should give us all positive or all negative solutions if a is less than 0. And this one should give us some negative solutions and some positive solutions. So we have certain features of these parabolas. So these are things that we've noticed before. So the vertex of a parabola is a local maximum or minimum point. And this is something we've already looked at in the context of quadratic functions. Here we have a vertex here. It's the kind of minimum or the maximum if we have a as being negative. It's the bottom of the valley or the top of the hill. You can think of that as being. And we can see those if r is even at the origin. So for power functions, where r is even, these can be found at the origin. If we look at the origin, on the other hand, of the ones where r is odd, we don't have a maximum or a minimum point. We have here what's called a point of inflection. So the point of inflection of a parabola at 0, 0, if r is odd, is where the function changes its concavity. And if you write this sentence down, I'll explain it in the next video because I'm aware I'm running out of time. But hopefully you're back in the depths of your memory. This word concavity is lurking somewhere, and in the next video we'll be able to bring it a bit more to the fore.